Okay, we have Ayush, who's coming all the way from India. He has a major in computer science and engineering, and he worked with Eva this summer, so I'll turn it over to Ayush.
Thank you. Hello, everyone. I'm Ayush, and I work with Dr. Iva Momcheva this summer on the 3D HST project. So the first thing, why do we need this big project of computer science here at the Astronomers? So the thing is, the data is getting bigger and bigger. You can't go traditionally to an observatory, get the data in your hard drive, reduce it, publish it, because with more and more advanced telescopes, the amount of data that we have is getting bigger. This is one of the images from the Pan-STARRS. They had to ship the data in crates from Hawaii. It was so big. And with telescopes like LSST and WFIRST, this is going to be even bigger, as you can see here. And that creates a bigger problem for us. You can't put the data on the servers and expect the astronomers to download that themselves and work on it, because it's too big for one single system to handle it. So that's why you need to give a reduced amount of data to the students, or to the astronomers for that matter. And that is not a very popular culture right now in astronomy, which needs to be developed. So that was the motivation for 3D HST project that we did this summer, is this data is quite large, and it would be a good platform to see how things in the future will scale. So it would give a good illustration of how we need to move towards data providing in future. So the 3D HST data, it's pretty complex. It has around 250,000 of objects with around 250 parameters for each one of them, apart from their raw images and the spectra, which comes to about 2 terabytes. And the survey is very complex. Just looking at this database schema would scare anyone away from the research. And that creates a very big and tough learning curve for anyone to start with. So before the start of the summer, we had some major project goals that we wanted to have an application programming interface, an API, with the basic searches, so that you don't have to download the entire data set and go through it yourself. You can just make one small line of command, and there it is in front of you. Then we also wanted to give users something of a web interface so that they can more interact with the GUI, so that they are more easily understanding the things that they are doing instead if someone is a very novice in computer science. And then we wanted to make all of this public on servers and then create documentation so that everyone can use it efficiently. Going to the specifics, we wanted to implement an object search, which was to search an object in the database, a near position search, which was to give the nearest object to a given position, a cone search, which gave a list of all the objects in the given radius, a coverage check, which told you if an object is inside the survey or not, and if it is, then exactly in which viewing tile. And then implement bulk searches, where you could pass a list of objects or upload a file and get the results all in one go. So this is what Eva gave me at the starting of the summer. This was a whiteboard drawing that she made 2 years back. And so essentially over this summer, we had to make this from a whiteboard drawing to a browsable web interface. So after 8 weeks, here we are with the API right now live at this URL. You can hit it up from your phones, your laptops, anything. And this is one line command which you need to find. And this will give you any object that you want. Just keep on changing the IDs here. And you can do this even from your mobile phones if you want, anywhere, without any big data access or anything. So this greatly reduces the time, the effort. The result it will produce will be there in front of you within milliseconds. Earlier, this process would have taken you maybe hours and a lot of resources, but now it's just there. Moving on to the other searches, we have all of these searches hosted live right now. You can do any of these searches. We also have a rich documentation which is also available for use right now, which has sample codes and user manuals for understanding how to use it and with sample test cases. So this is a web interface that we created. It has a list of the 5 searches that we currently host. Clicking on any one of them will give you a detail about that search, and clicking on this links will direct you to the search page, which looks like this. Now you can either do a search one at a time, you can copy paste an entire list here, or you can upload a file and then get the results like this in a table. And the good part about this table is you can just do a CSV download or Excel file, PDF, print it, copy on the clipboard just by one click. So it is all making like, instead of downloading like 2 terabytes of data on your system, you can just do it by one click right now. So for the future developments of the API that we intend to have, so we want to return the full photometry data, the stellar masses and whatnot for individual objects as well as for near positions. Then we want to return the 2D and the 1D spectra and return the thumbnails in any band. For the web interface, we want to implement more advanced searches so that you can have more detailed result about an object, because we obviously have that in our database and we would like audience to have that. Then we want to display the data for an individual object on one single page, like a Facebook or a Twitter timeline where you could see individual objects with all its information dynamically generated on the fly, which would look something like this, which would have all the data, everything there, and with the real image. And this will all not be saved inside the database. It will be generated on the fly, which is really good because it saves us a lot of space in the database. And then we would allow this to be downloaded as a single file. And then the last one would be to tie this to a map interface, so you could actually see where this object is in the sky. And that would give a good sense of idea, like where exactly the space is, where this object would be. And as Iva mentioned in her talk yesterday, that there could be many possibilities with this rich data sets. Thank you. Questions?
Ayush?
Yeah.
If you had to extract information from massive data to make the thing work fast,
Sorry?
did you have to extract information into sort of pre-compiled lookups for it to be a fast response?
So right now, Eva had a database inside SQL servers, and we are pulling the data from that using the SQL Alchemy in Python. So if we have data somewhere else, we can easily do that. That's not a big issue.
But you don't have to pre-process the database
No,
itself.
no, no. Yeah.
What's the total size of the target database?
It's 2 terabytes.
Number of rows?
It's 250,000. That's right. Yeah, around 250,000 objects.
So, do you think that your stuff will be able to scale to hundreds of millions?
I have problems with that. It would not scale with SQL, that's for sure, because SQL is not very good at scaling. But we have discussions about it, like how should we move if we have to scale these kind of servers. And we have a few ideas with the databases that we could use. There was one developed last year called SciDB. It's developed in MIT right now, which is pretty good at scaling. I tested it last semester in my college. And there are pretty more servers coming up which have pre-processing capabilities which do the service asynchronously. So even if you're not searching, it will like keep on implementing better models. Yes, Thomas.
So is the bulk search implemented into the API call?
Yeah.
You
Yeah.
can pass file reference into it?
We are using the post request right now. Post request.
Okay.
Instead of a get request for one object,
Yeah.
you are using post request for multiple objects, because it really scales down the time to get the results back.
Yeah.
If you do a get request with multiple objects, it takes around like 10 seconds for 100 objects, which I tested. But if you do a post request, you can get that in like 1 second. Yeah. Yeah. That's what I wanted to explain. That's an API call. So API is an application programming interface. I don't know if everyone is familiar with that. So an API is like a middleman between you and the database, or anything for that matter. It could be a Google search. It could be entire worth of the internet. So when you go to an API, so this is what I did yesterday to explain this. This is a Twitter API. So Twitter has an open service. You can just fire up an API query. So you don't have to actually have the data of the Twitter. You just need to tell them, I need this data. And it is the responsibility of the API to find that data, to process it, and you just have to worry about getting the data back. And then you can do anything you want. So yesterday I did this with the James Webb hashtag on Twitter and got the results like this, just to show you around. So API reduces a lot of processing at your end, and the user is safe from using a lot of resources, which saves a good amount of money and time. So these things will definitely be needed more and more as the data sizes are becoming larger. Yes, definitely.
You said at the beginning, this started off on the whiteboard when you got here this summer?
Yeah, that whiteboard was made 2 years back by Yes, Thomas?
So when you have back to the API call, when you have the API call, does it return as standard output, or what's the format of the?
It's a JSON response.
Okay.
And we have the documentation ready where you can like browse through what features does it return, and we have error handling and everything done. We also have a rich metadata responses so that you can know what actually the query went when it went inside the API, so you can like easily get the error messages too.
And that's all in the JSON output?
Yeah, it's all. You can like go through the documentation. It's right now live if you want. Yeah.
What was the motivation behind the name?
Eva, would you take that?
All the servers in the survey have been named for single horned animals, so we had used for rhinoceros and narwhal. So this is the next one, I guess. So the API kind of gathers all the outputs from the survey and gives it to the users, so that was a multiple one.
Thank you. Any more questions? Yeah.
So like for some of these searches, like objects and so on, like what did you use as a key? Like what were you?
Yeah. So like here, so this is the endpoint which is called object, and you then provide an ID, and this is your ID. When you are doing a cone search, you provide an array and a deck and a radius in which you want to search, and these units in array, this could be anything. Any units that you can input and get the output in AstroPy, you can do the same here. It supports every units. And as for the radius, so right now we have dealings in arc minutes, so you can input 1 arc minute, 10 arc minutes, and see all the objects in that. Yeah.
Any other questions?
Thank you.
Okay, I don't know how we keep doing this for keep being ahead of time, but we're actually switching topics. We will now switch to outreach and presenting science to the public. So I will introduce to you Ryan, who worked with Christina Oliveira, Joel, and I this summer, and I'll turn it over to Ryan.
Hi, everyone. My name is Ryan Logue, and I'm here to talk to you about spectroscopy, which is undoubtedly an important part of modern astronomical research, but it is also notoriously difficult to explain to the public. I mean, after all, it'd be really nice if your average person was as interested and intrigued by the spectrum of a galaxy as they are of an image of it. After all, it's said that if a picture is worth 1,000 words, then